So today I'm going to present our team solutions for the Coleridge initiative, source data competition, which we finished first place. So I'm going to talk a bit about our team and the competition in general. A few key points about our solution, all the traits in preprocessing and post-processing. And the most important part, I think, is the modeling process, which I think our team made is quite unique, and it can be a little bit complicated. Okay, so about us, we have two members. We are colleagues. My name is Khôi Nguyen. I'm a data scientist at the VNG Corporation in Ho Chi Minh City of Vietnam. And my teammate is Nguyễn Quang Anh Minh, even Khôi at Minh, and he's an AI engineer at the very same company. Okay, about the competition, the goal here is to identify data sets used in scientific publication. And I think the goal is simple enough, but this competition is particularly challenging. So first of all, the training data is not fully labeled. And with all the labels that we have, the amount of unique labels very limited. We have, if I remember correctly, 130 unique labels, but many of them are actually like aliases of the same title. So the real number is even lower. Then we have problem with validation. So in problem like this, you usually want to split data in paper by paper, publication by publication. But the problem here is that one paper can refer to many data sets, and one data set can be referred to many papers. So it's almost impossible to make a clean cut. So that say is absolutely no risk in the training process. And then we have the public leaderboard, which I think is main sources of pain for us and many other competitors, because a large portion of the public leaderboards was overlapped with what in training, but this doesn't hold for the private leaderboard. So the score in a public leaderboard is always like overestimating the real performance of the solution. And finally, the matrix with the F0.5, which is forced us to be very precise about every predictions that we make. And about our solution, in the key ideas for us was to use the contact information instead of the label themselves, which were very limited, as I explained. And in the end, we actually came up with two solutions. The one that I presented here is the winning one, with score 0.576 on a private leaderboard. And we also have another one, which could have been the third place solution. It scored 0.565, and I made a write-up for that in the forums if you're interested. In the end, we could not find a way to combine these two solutions together. So we have to submit them separately. Both of these solutions share the same pre-processing and post-processing function. We want to use them to normalize the labels and the predictions. The tool we used were mainly the transformer libraries by Hugging Face and Spacey NFV, so nothing special. About pre-processing. So as I mentioned, the training data has a lot of missing titles. So there are a few ways to fix that, and I think a few teams actually manually try to label anything that they can until they have enough data to train. And we kind of did the opposite. We use a few rules to find anything that is possibly a data set and remove all of them for training, so that in the end we only use what was originally given to us. And the tool we used was Spacey Review Detector. And how did we do that? So we noticed that the first time a data set is mentioned, it's usually a pattern of its the full name, followed by the abbreviation in the parentheses. So we try to find anything like that in the training data, and if it contains specific keywords like data sets, a database, study, we treat them as a possible label, and we remove all of them from training. We use them for validation. A few normalization rules. If we find a mask in the form of full name followed by abbreviation, we also add the full name and abbreviation to the list of labels for the sample. And if only the full name is found, we try to find the abbreviation too. And if we found it, it's also added. And finally, we remove from training any sample that contain any label that belong to both the training and validation set. So to avoid any list. And come to modeling part. So in case you're not familiar with deep learning for NLP, we are using a few variants of the BERT architecture, which is a transformer language model. So basically what it does is, for a sequence of input token, it will try to map each of these tokens to a vector, which we call an embedding. And this embedding is special because they will change depends on the context surrounding the token itself. So aka contextual embedding. So this is basically all the feature engineering that we use. We need to introduce a few more terms, query and the subprocess. So what is a query? It can be seen as the new unseen data, like the text data, and it's a chunk of text that potentially contains the dataset title that we want to extract. And then we have the subprocess, which is basically our training data, right? It's called a set of samples with annotated labels, so we know that they contain dataset title and where they are in the sample. So with a new query, what we do at a high level is that we want to look into the process, and we want to see if there are any patterns in those support samples that's similar to what the query we are currently having. And if we found a pattern like that, we know how to extract the information. So this is a bit technical. There are only a few things you need to pay attention to. So this is the query, right? It's contain. So in case this query it contains a label, it may not contain anything. So we want to look at any token that belongs to the label, and we take the embedding of each of those tokens, and we take the average of that to make a representation for the label. And we look at all the tokens that does not belong to the label, and we do the exact same thing, and we create the embedding to those tokens too. For the support set, we need to have an extra operation with the masking. So what masking does is that we replace the labels inside the sample with a generate mask token. And we do almost the same thing with the queries. It takes the mask embedding of the mask token and the non-mask embedding, we see the embeddings of all the tokens that do not belong to the mask, that's not the mask. So we have the label embedding, the non-label embedding, the mask embedding, and the non-mask embedding. That's the pause 14, remember. So this is I think the key idea. The mask token is a generic token. It has no meaning by itself at all. So when we force the model to find the embedding of the mask token, it has to pull the information from the context surrounding it. On the other hand, the label itself, as you can see, is very distinct meaning. I mean, if you look at that, you can possibly guess like 95% or something that this is a dataset title. You don't need to care about the context itself. So this means that the connection of the label embedding to the context is weak. On the other hand, for the mask embedding, this connection is strong, and we want to make this embedding as close together as possible. We want them to be similar. So by doing that, we are forcing the model to look at the context surrounding the label when it looked into the label, even when it had no reason to do that. And to do to enforce that, we use a loss function called argface. We can explain it later. So this, as you can see, this is basically classification, right? So we have two classes. One represents the mask and the label, and the other the null mark as non-label. We can use your softmax with cross entropy, but it doesn't always guarantee these embedding to be clustered close together like this. And this argface loss function, I think, kind of guarantees that. It was originally used in face recognition, and it's working really well. It's worked much better than softmax. Okay, so this is just kind of the secondary objective. We haven't offered any prediction yet. So to make a prediction, remember that we extract the mask embedding, and we also have the representations for each token of the query. So basically what we do is we try to find the cosine similarity of the mask embedding to each of these token embedding. And the higher cosine similarity, which means it's more likely for its token to belong to a dataset title. And then we normalize them to be in the range of 0 and 1. And since we have the graph shoot, which is just a binary sequence, which 1 means that it does not belong to the dataset title, and with 0 means it does not belong to the dataset title, and 1 means it belongs. This is just binary cross entropy, binary classification. We just use the binary cross entropy loss function as usual. And you see for training. So for inference, it's more simple. We don't need to go with the mask label embedding and argface. It's just for training. So here we do exactly the same as the previous step. We also get the output and we apply a threshold, and we take any subarray of consecutive ones with a length of, I think, more than 4, more than 3, and we have the prediction, the final prediction. For training methods, we use a single GPU, so the batch size is really small, it's only 4, and the size of the support set with the set of samples for training is 3, and for inference is 100. There are a lot of negative samples in the training data, so we always use 1/8 of them. We use a few argumentations. I think the most important is random label swapping. It means that we randomly replace the training label with labels from the ARC datasets and the old competition big context datasets. We also do random word dropping, which means that we drop the last word from the dataset name if it's with an abbreviation. And you see abbreviation to be more exact. We randomly convert the dataset name to lowercase, but keep the abbreviation intact. So the final solution when ununionizes an ensemble of two transformers based on two architecture, biomet roboter and cyber. So basically what we did for example, we changed the backbone, which is a feature extraction module. And we take the final result of the two model and we unionize them together. About our post-processing, we remove any invalid reasons, which are reasons that contain incomplete words, like subwords that is not a whole word, like from national study of use, and the model output this string is not valid. And we also remove any reasons that were too short. We also only take anything that appear at least twice in a test corpus. But the solution is not very sensitive to this threshold. We try to take things that appear at least twice, 4 times, and the score doesn't change very much. We also try to make a database of all dataset titles we found. on the precision of the model, and we try to remask them with this test data. The idea is sometimes the model can detect a data set in a particular context, but in another context, it cannot, because the context is not always clear. So we find all of them and we mask them with, basically this is just string matching. And if a data set title is found, we also add this abbreviation to the predictions. And since I spoke about in the beginning, the public leaderboard is not very reliable because of the overlapping. So to better assess our performance, we try to remove anything that is similar to what was in training. And we found that the performance of our model is correlates quite well when we submit with that post-processing. And in the end, we trusted the public leaderboard. And the validation, it kind of worked, but it's never good enough. Okay, I think that's the solution.